Hi everyone. So the goal of this video is to understand the force of gravity. So I want you to be able to explain the force of gravity and the normal force and calculate the force of gravity. So as usual, before we start, find a good spot in the classroom or wherever you are so you can focus on the video. Make sure you have a copy of the guide notes and the use of headphones is suggested. And again, the useful tip is you can change the playback speed in the bottom right corner on YouTube. So if I talk too fast or talk too slow, change the playback speed to help yourself out. So gravity. Gravity is a force. It's one of the major forces in physics. And for us on Earth it's just pulling objects towards the center of our Earth. All right. Gravity makes objects accelerate downward. And the acceleration of gravity is a constant. It's negative 9.8 meters per second squared. So remember, those are our units for acceleration. It's negative because it's in the downward direction. It's making objects fall, move in the negative direction. So we have a negative number. All right. And that is actually true for all objects. One thing that we might have mentioned in the beginning of the year and shows up again here was that it doesn't matter if an object is heavy or light. There were some famous experiments done a very long time ago, especially there's kind of this legend about Galileo where he dropped two objects from a very tall tower, and one object had way more mass than the other. But he found that they fell at exactly the same rate and they hit the ground at the same time, showing that heavier objects don't fall faster than lighter ones, and that gravity affected all objects equally. So we are able to use this constant of negative 9.8 meters per second for all objects that are falling towards Earth. And not even just falling towards Earth, but just anything that is attracted to the center of our Earth, we can calculate the force of gravity from that object. So in physics, mass and weight are not the same thing. And we can't just use those terms interchangeably from here on out. We have to be very specific about which term we are using. And in physics, we can measure mass in kilograms, but we measure weight in newtons. So if you're talking about how much something weighs, you really should use newtons. And if I was going to try to calculate the force from gravity on an object, I would use a very similar version of our equation of force is mass times acceleration. Like if you look at this equation that I have here, it looks a lot like the equation that you probably already have seen, where we have F, so we have a force equals a mass, and then the equation that you see on your screen it says g, but g is just a way to kind of say the acceleration from gravity. It's a very specific type of acceleration. All right, and again, that acceleration is negative 9.8 meters per second. So for example, what is the force of gravity on a 10 kilogram object? Well, we don't know the force, that's what the question's asking. We know that the mass is 10 kilograms, and the acceleration, which isn't given to us in the problem, but again, we can always assume that the acceleration is negative 9.8 meters per second squared. Right? Whenever we're talking about the force of gravity, that's the number that we want to assume. All right, so from here, if you were trying to calculate this, you would just say, okay, force is equal to ma. You can say ma or you can say mg, however you want to say that. But that's going to be 10, because that's our mass, times let's see, negative 9.8. All right. And if you multiply those two together, you'd get negative 98 newtons. All right. So the force of gravity on the object is negative 98 newtons. All right. And then one little distinction here, again, about mass and weight. And the reason why this is important in physics is, or one really good example is imagine that you are on Earth, but then imagine at some other time you're on the moon. Okay, when you're on Earth, and let's say this is you, all right, when you're on Earth, you are 80 kilograms, okay? And then we can do a little bit of math and we can figure out what is your weight in newtons, right? We can multiply it by the acceleration. We can figure out your weight in newtons. Now, if you go to the moon, you're still 80 kilograms. Your mass has not changed, right? Your body hasn't changed unless you like have lost some crazy amount of weight before you go to the moon. You're still going to be 80 kilograms, but you will not weigh the same. Your weight will be much lower because the gravity on the moon is way less. So on the moon, you would still be 80 kilograms, but your weight would only be 130, 131 newtons. All right, so that's just a really good example. I hope that's a good example for you to see how mass and weight are different. No matter where you go in the universe, you have the same mass, but your weight might be very different depending on the force of gravity on whatever planet you're on. I don't know, some of you are young enough that maybe one of you will go to Mars one day, and your weight on Mars is going to be different than your weight on Earth. All right, so why don't things fall towards the center of the Earth? We've talked about this force of gravity. We've talked about things pulling you down, but why don't we just fall towards the center of the Earth? If this is the force that's acting on us, what's stopping us from falling? Well, you could say the floor, and technically that's true. So what we say is that the floor and whatever object you are standing on or whatever is there is applying this thing called the normal force. All right. So gravity pulls objects down. What stops them from falling towards the center of Earth? We say the normal force. All right. And so over here I have a picture that kind of shows you we have a normal force that is pushing up. All right. It's kind of like whatever surface you have here. It could be a table, it could be the ground, but it's applying a force up that is equal and opposite to the force of gravity. All right. So the normal force is the force that the ground exerts on objects, and it is equal and opposite to gravity. All right, another type of force that's important to understand is tension. Tension is a force exerted through a rope, a string, a cable, a chain, whatever, some kind of thing that is hanging from the ceiling or whatever. All right, and if an object is hanging from a rope or a string or a cable, its weight is balanced by the tension force. So you can kind of see in this picture here, let's say we have a mass that's being pulled down, its weight is going down, right? The acceleration of gravity is pulling it down. The tension in this cable is equal and opposite to that weight, so that the mass is not moving, it's not accelerating. Right? The tension and the weight are equal and opposite, where the string or the cable is strong enough to hold up the mass of the object. And then one other thing I'll mention here is the force of gravity. So this is an equation that is slightly different from what you've seen, but basically this is an equation that applies to any object in the universe. So when we talk about gravity from the Earth being attracted to the sun and how the Earth goes around the sun, or any object, especially in the universe, we can use this equation. So it basically says that the force of gravity between any two objects comes down to a gravitational constant multiplied by the two masses that you're interested in, and then divided by the distance between them squared. So for example, if I wanted to know the gravitational force between the Earth and the Sun, well, I would take this gravitational constant, which is a very small number, but it's a constant for this equation. I would take the mass of the Earth multiplied by the mass of the Sun, and then divide it by the distance squared. How far is the Earth from the Sun? And I would square that number. And if you do that math, then you would find the force of gravity between the Earth and the Sun. You could even do it for regular objects like us, and you'll find that the numbers are very similar to what you would have gotten if you just did force is mass times gravity. For example, you could take the gravitational constant, and your two masses could be Earth and then you. And you could divide it by the distance between you and the center of the Earth. And if you do that, it might be a little fun experiment for some of you who are curious, but if you did that, you would get the force to be 9.8. Um, so maybe give that a shot if you were so inclined. But this is the gravity equation that applies to all objects in our universe. All right, so hopefully that was useful. Hopefully that made sense. I will give you a few practice problems on calculating force in different examples, and I'll probably make another video to kind of show you how to do some of these equations. But I think that's the basics when it comes to the force of gravity.